All right, good morning. So welcome back. All right, any questions up to here? I want to go through pseudocode for search, delete, and add today, and then we're pretty much done with PA1. All right, everyone good? All right. All right, I'm going to post an announcement after class just to highlight this, but let me mention something that's really important. I've discussed this before, but let me make sure everybody's clear. When you're doing your functions for add, search, delete, and print, you have to be treating the linked list as a linked list. For example, theoretically, you could do a search function by searching the array of struct nodes. You could just go from 1 through 99, look for a struct node where the data value matches and the valid flag is set to 1. You're not allowed to do that. Okay? The only way you can do search, add, delete, insert, start with the sentinel node, follow the trail of nodes from one node to the next to the next. Okay, we're going to go through some pseudocode for search first, and you'll see, an example of doing that. But you gotta treat this as a linked list. Okay, I want you working with the data structure. You're not allowed to take advantage of the fact that you know how it's implemented, and I could just do a search from 1 through 99, right? That's not a valid search function. And this is tied into something we talked about when we first began this a week ago, which is the idea of an abstract data type. Okay, so the above routines, add, print, delete, search, represent the interface between a main program and the linked list as an abstract data type. So to add a node to the list, create a new node, search the list for the proper point to insert the node, adjust the prior node's next field to point to the new node, and adjust the new node's next field accordingly. Similar actions are taken for printing, searching, and deleting as discussed in class. So you're always going to do these things by starting with a sentinel, moving down the list, getting to some point, and then taking some action, for example. Alright, also if you know how to use recursion, you're not allowed to do these recursively. Right, there's a really easy way to do an insert function or a search function and so on using recursion. I don't want you doing those. I want you to follow the chain of links from the sentinel to the next node to the next node and so on. The reason for this is because we want to learn linked lists, right? We don't want to just have something that lets us insert things and retrieve them. We want to learn linked lists. And the reason we want to learn linked lists partially is so that when we get to PA2, we don't have to try to figure out what a linked list looks like. What does a sentinel node look like? What does it mean to insert something, right? We want to have some experience with that so that in PA2 we can concentrate on the new parts of the assignment, which will be, doing a malloc, doing free when we delete, using pointers, getting comfortable with ampersands and periods and arrows and things like that. Ask me, recursion. We will get to recursion. I'm not going to write it down because someone will take it and run with it. But how do you search for a number in a linked list? Well, if the list is empty, it's not found in the list. If the first node in the list is the number you're looking for, it is found. Otherwise, search the remainder of the list, right, with your search function. So just pass that to your search routine. And you can do the same thing for insert and delete. But we'll definitely do tons of that when we get to binary trees in a few weeks. All of the stuff we do with trees is going to be recursive. And by that point, we want to be very comfortable with not only the basic ideas of some data structures like linked lists, but also with, you know, how we write code to manipulate memory, and how we do the mechanics of malloc and free and pointer indirection and so on. And then we'll get into the heavier recursive algorithms for dealing with trees. So there's a lot of stuff ahead of us. It's a really fun pathway, I think, because you come out of the other end of this just, you know, a much higher level power programmer, basically, where you can really go in and you can just sort of like manipulate the memory of a system how you choose. So we'll get there. It'll take a few weeks, but we're on a good path here. Let's see. So question, when we print out the linked list, all the ones that don't have a value are assigned as 0. Should those get printed too? So when you print the linked list, you're never going to encounter invalid nodes, because how are you going to print the linked list? You're going to start with the sentinel node. You're going to follow it to the first node of the list, print that. You're going to let that point you to the second node and print that. And you're going to keep doing that until you get to the last node of the list. You print that. You look at the next field. It says it's my null. You're done. So you absolutely do not want to print by just going through your array and looking for things where the valid field is equal to 1, right? You print by going through the list. And we did actual code for that yesterday, right? And nowhere in that code did I iterate through the array of struct nodes, right, except in the initialization routine. The print routine just starts with the sentinel, sees what it points to, and just moves down the list. A really, really important point there, right? Don't be trying to do search and print and delete and all of that by barehandedly handling the struct node array. Right, do it all using the notion of a linked list. All right, so let's do our search function. We did print yesterday. We did code for print. Let's look at our search function. So we're searching for some number n in our list, and let me draw a picture here. This is kind of my go-to linked list when I work with these. So here's the sentinel node, points to a 10, 20, 30. I'm doing that because I have a node in the middle, so I'm not worried about, you know, first node, last node edge cases. And let's suppose we're searching for the 20. Okay. The way we're going to do this, we're going to basically start with the node the sentinel points to, and I'm going to think of this as my current node. And I'm going to see if that's the number I want. And if it is, I'm done. I can come back and say, yep, found your number. If not, I'm going to use the next field to change current to point to that next node. And I'm going to see if that matches my data. If it doesn't, I'll use the next field to move to my next node and see if that matches the data I'm looking for. All right, so let's see. So what's the body of my loop going to look like? And I'm going to this is pseudocode, right? So I'm going to write down the idea of what I want rather than the mechanical, you know, C code that will make that happen. What I'm after, the spirit or essence of this, is if the current nodes data is equal to n, then we found the number we're looking for. And I'm going to say, yes, the number is in there. I'm going to make a note here, though, because remember, current is an integer. So if I'm actually coding this up in C, I can't say current.data, right? Current is an index into our array. And so, you know, here's my ignore section. Maybe we're doing search. And we're passing in a struct node array and an integer n, right? And so instead of current data, I would say something like ll bracket current dot data equals n. So that's a comment within a comment, right? But I'm going to use this notation, right? Because I don't want to be thinking about C. I want to be thinking about the algorithm itself, right? So if the current data is equal to the number we're looking for, we're going to say, yep, we found the data. Otherwise, what we want to do is move current to be the next node. Well, if current is right here, how do we find the next node? It's the next field of current. So it's just current equals current dot next. And I'll translate this one more time for you, and then I'll stop translating here. But this would be something like current equals ll bracket current dot next. All right, got the idea? So there's pseudocode and there's C. So let's concentrate on the pseudocode. So this is all going to go inside a loop. And this is going to keep moving current down from node to node to node. But there's a possibility that our node is not in the list. Maybe we're searching for the number 50 and it's not going to be found. So how do we know that we're done searching? Well, when current comes down to here, the last node of the list, it could be we're searching for a 30. So we still need to see if that node's data is equal to n. And if it is, return yes. All right. Now I could put a check right in here, which says, you know, if current.next equals my null, then return no. But there's other ways we can do this. If I put this in an infinite loop and I put an exit condition right here, that may seem good, but if I put this in an infinite loop, this is always going to execute, which means it's going to look at the sentinel nodes. It's going to look at the sentinel nodes data potentially if our list is empty, right? If our list is empty, I never want to do this check. I don't have anything in the list I should look at. So now I have to put in some extra condition before my infinite loop to say, is the list empty, right? So let me suggest a different way to manage this exit condition. If we've just checked the last node and it didn't match our data, current is going to get set to whatever that current node is pointing to. So current is going to be changed to my null. And that's a condition we can use after this to exit the loop. So if we put this in while current is not my null, right, that will run great. So someone suggested, well, current next is not equal to my null. So we can't do that here. We might be able to do it somewhere else, but we can't do it here because if we check that condition right here and our list only has a single node, and this was my null, we would be exiting our loop before we had checked the 10. But we could, you know, theoretically put a check right in here after we've already checked the data to say if current next equals my null. But then again, if this is all inside an infinite loop, it's going to do this comparison at least once, which we don't want to do if the list is totally empty. So spend some time thinking about how you want to make this work, and then draw pictures and test edge cases before you open VI, right? Before you actually start coding it. Because it's a lot easier to make changes in your algorithm in pseudocode on paper than it is to you know, try to modify your implementation in an editor. And think about edge cases, right? So here's the action part of the loop. Here's a suggestion for a termination condition, right? We need to initialize this still, so you got to have initialization, a loop, and a way to exit the loop. And then think about edge cases. What if we're trying to find the first thing? What if we're trying to find the last thing? And what if the list is empty? I think those are the 3 edge cases. All right, so how would I seed this? Well, we want current to start off as the first node, so I would probably seed this with current equals, you know, LL0 dot next. So the first current always equals list0.next. Yes, exactly. And if you want to be polite about this, right, you could actually do something like, you know, think of this as a sentinel, set it equal to 0, and then set current equal to LL sentinel dot next. And now I'm kind of thinking of this as like, you know, the next field of the sentinel node, right? And I'm getting rid of that magic number in here. So play around with that. Okay, so what does this do in our edge cases? If we're looking for the first thing in the list, we're looking for a 10. Well, this is going to start off with current equals here. Current's not my null. Current data does equal our number. We're going to say true, and we're good to go. If we're looking for the last thing in the list, this loop will continue until current is right here. It's not my null. It'll check the data, see if that matches n. It does. We're still good. If we run out of nodes, right, that was the case we started with, current will change to my null. We'll kick out of our loop. If we come out of our loop, then our data is not found. So we just say no. All right, last edge case, empty list. Empty list, the sentinel points to my null. So when we do this initialization, current will be my null. The while loop will never fire. We'll come right down here and we'll say your data is not found. That works great too. So that should work for all your cases. All right, any other questions on that? So let's do delete. Delete gets a little more interesting because we need to manipulate 2 nodes in our list to do a deletion. So let's delete the 20. And even though I'm working with a list with 3 nodes, if I delete a node in the middle, presumably it doesn't matter how many nodes came before and how many nodes came after, right? The question of edge cases is basically, is there a node before this? Is there a node after this? If there is, it probably doesn't matter if there's 1 node or a million nodes after it, right? If my code works in this case, it should work no matter how big the list is that I'm in the middle of. But then we're still going to need to look at, you know, deleting the first, deleting the last. So in your write-up for delete, you notice delete is a void, so it doesn't return a value. You should only call this function if the number is contained in the list. So delete cannot fail, right? You should never call delete with a number that's not in the list. So it's like print. Print is going to take the list and do something. Doesn't matter if the list is empty or not. It's always going to succeed. Same with delete, right? As long as you call it with a number that's in the list, it's always going to succeed. So we don't need a return status. But your main program, remember, lets you say I want to delete a number, and it can return a message saying node not found. So how do you know the node's not found? Your main program has to do that check. And at the point of writing your main program, this is trivial, because what do? Well, you already have a search function. So if someone says delete 15, first thing you do is search for 15. And if it's not there, print out node not found. Which is different from not found, right? This does not get printed by your search function. This gets printed by main. This does not get printed by your delete function. It gets printed by main, right? All of your functions do something and they do it silently. And if something exceptional happens, they return a value to indicate that. Okay, this is another part of this firewall between the code and the implementation of the code's algorithm. So your main program, before you respond to a delete request, should call search and then print out a message. All right, so let's say we want to delete the 10. All right, let's delete the 20. So node in the middle. So same thing as with a search, but we're going to need a pair of pointers, because when we reach the 20, right, and we see that the data is equal to what we're deleting, we need to adjust something in the previous node. So we're going to have a pair of pointers. We're going to have a previous and a current. We're going to check the current node's data. Doesn't match what we want. We're going to move these down so that current is 20, previous was the node right before. Now we're going to say, oh, that's the node I want to delete. At that point, we need to adjust the previous node's next field. Well, we can find the previous node because we've got a variable that's holding that index for us. And so we'll change the previous to point to the 30. That deletes the 20. All right, so main body of our loop. If current data equals n, how do we remove that current node from the list? Well, we want to change the previous node to point to what the current node is pointing to. That's all it takes. Just set previous next equal to current next. All right. And then we need to change the valid to 0. And how do we change the valid to 0? Call release node. And release current. So that sets valid to 0. And we can return. Can you avoid using previous pointer by checking next data on each iteration? You can, but you're going to get into edge cases. You're going to have to look ahead one spot, basically. And before I move to the 20, I'm going to see if the next node is equal to 20. And that's doable, but it will get you into, I believe, an edge case when you're at the end of the list. And so I think it's a lot cleaner to keep a pair of pointers. our goal in computer science is always not to have to think too much, right? So make a pair of pointers, move them down, and then, when you want to do something, well, you've already got some pointers telling you, what these different nodes are, and you can just kind of put them together like Lego blocks or something. Keep things relaxed. But it's an interesting exercise to try to do it without a previous pair also. Is it okay if I use release node instead of release underscore node? I think it has to be called release underscore node. Let me see, grading. Release underscore node is worth 10%. Yeah, that would probably cost you 10 points. Maybe not. But yeah, call them the same thing in here. The reason being that, if there's something going on in your code, and I need to dig into it deeper, right, I might start linking your code to my own main programs. And if I have to rename what I call functions and stuff, then that's not going to be good. All right, so that's the body of our delete function. Yeah, and at some point, that's cool, you've been doing that to help some people. At some point, I may switch over to not having you write a main program, but have you just submit your package of functions. And this is something you'll typically see when you get to university. You're basically supplying functions, and the instructor will link those in with their own test bed. So that's a little bit of the ODP setup too. All right, there's the body of our delete. Where do we exit? Well, I've said that you're not going to call delete unless the node exists. But suppose we didn't have that constraint on here. Suppose it was possible that you tried to delete, 55 and it's not in the list. We would get to the point where this was previous and this was current, right? And well, let's move down the list first, right? So if this is not the node we want to delete, move down the list. So set previous equal to current, and set current equal to current next. So if 30 is not the node we want to delete, we'll change previous to current, and current will now be equal to my null. And that's our indicator that we're at the end of the list. So if we were going to check, for the case where you're deleting something that's not in the list, we could again do while current is not my null. It's up to you what you do if someone calls your delete function on a number that doesn't exist, because it's never supposed to happen. But be careful what you decide to do. So I wrote some code for a company once, and there was a case like this where something should never happen, but I wanted to do something, in the case where you happen to come out of this loop. I couldn't sleep at night unless I put something in there. So I had it print a message saying, "Rip in space-time continuum, eat hot death pig." And 2 years later, I was gone from the company, but they upgraded their operating system, and this condition that shouldn't have happened could now happen. And one day, somebody got a message from the accounting package saying, "Rip in space-time continuum, eat hot death pig," and yeah, so that was good. So you can put a condition on your while loop if you want, but you can't return a value, so you just return at that point. All right, so we've got the body of our loop, we've got the action item, we've got the way we're moving down the list if we're not ready to take action yet. We've got an exit condition. How do we initialize this? The first node we want to check is this first node of the list. And it turns out, because we have a sentinel node, if we start off with our previous node being the sentinel, this will work perfectly. because if we want to delete the first node, if we're going to get rid of this 10, what's the thing that we need to change? It's really the sentinel's pointer needs to point to the thing that came after the 10. So if previous starts off as a sentinel, previous next equals current next will still work great. So we can seed this with previous equals 0, current equals previous next. And the last thing to check maybe is if we're deleting the 30. So we're going to march through until previous is the 20 and current is the 30. Current's not my null, so we're still going to go into the body of our loop one more time. If current data matches what we're deleting, yes, this will set previous next equal to current next. Well, current next is equal to my null, so this statement will set previous next equal to my null. And then we'll release this node by calling release node and return, and again that does the right thing. All right, questions on that? All right, let's do our add function. So this is slightly trickier than deletion, only in the sense that instead of looking for the number n, we need to find where we should insert this. And since our list is always sorted in increasing order, we should insert before the first node that's bigger than n. And here again, the only thing that insert can return, the only error code it returns is if you run out of space. Right, sorry, the add function. Add returns 1 if successful, 0 if there's no space left in the array. Now, the main program says you should not have a number in the list more than once. So again, your main program should call search before you call add, and make sure your number is not in the list. And if it is, have your main program print out the error message. Otherwise, we can go ahead, we can go into our add function. All right, so going to use a pair of pointers again, because if we decide we need to insert right before the 20, we've got to adjust the previous node's next field. So we're going to do a pair of pointers, and let's just, for working purposes, let's try to use the same loop structure and initialization that we used for delete. So let's do previous equals 0, current equals previous next. And you'll notice in all of this stuff, right, we always start off with a 0. That's the sentinel node. Right, so this is the sense in which the sentinel is kind of a handle to our linked list, right? It's the thing that you grab onto that gets you all the rest of your data structure. We've got, a zillion nodes pointing to other nodes and so on and so forth, but to grab all of that, all we need is this sentinel node, which for PA1 is always at location 0. It'll be different for PA2, but it will still be the same concept that if we know the sentinel, we have access to the whole list. All right, so we'll set previous to the sentinel node. We'll set current to previous next. So here's previous, here's current. And we're going to have some kind of loop. And inside this loop, we want to know, is our number smaller than this node's data value? And since these nodes are increasing, right, the first time that condition is true, that's going to be the first number bigger than our number that we're inserting. So if current data is bigger than n, then we want to insert before current. So let's say we're adding a 15. We're going to want to put it right here before the 20. So we'll start off, 10 is not bigger than 15. We'll move down, 20 is bigger than 15. Insert right before that. All right, well, before we do all of this, let's make a new node. So how do we make a node? We draw a box, we put a 15 in there. And I'm going to call this new. And so new is going to be get node. So we call our get node function. That will do the job of searching for an entry in our array with valid equal to 0 and returning its index, and also setting the valid flag equal to 1. We don't have to worry about those details here. We want a node, we call get node, it gives us a node. Okay. We need to add a check to make sure we didn't run out of memory. So put in a check here. If new is equal to my null, then return to 0 saying we can't add. And your main program can pick that up and inform the user. So I'm not going to worry about that here. So new is our get node that makes this box. We need to set the data value. So new dot data equals whatever we're inserting. I'm just going to call it n. All right, so now we've got our box with the 15. Now we've initialized previous and current. We start iterating through our loop. If current data is bigger than n, then we're going to insert right before. So let's suppose we've gotten to this point where the current node is 20. So how do we do this insert? We need to change two things. We need to change this node to point to our new node, and we need our new node to point to what the previous node used to point to, which is current. So change the previous node to point to the new, and change the new nodes next to point to the current. And then just return your success value. All right, so that's the action part of the loop. When we decide we're inserting right before current, basically have the previous point to new, have new point to current. That sandwiches it in between those two nodes. If we're not at that point yet, though, if this was our current node and it's not the right place to insert, move down the list. So set previous equal current, and set current equal to current next. We could also set previous equal to previous next, but we know that current is previous next, so you could do it either way. All right. So what's our termination condition? Right? Because as long as we find a place to insert in the list, we'll eventually satisfy this condition. We'll go ahead and take these actions and we'll return from our function. But what's going to happen if we run out of nodes, right? This is moving us down the list. If we do that forever, eventually we're going to fall off the edge of the list. And that's the case that's going to happen when we're inserting something that's bigger than the last node. In other words, we're trying to add to the end of the list. So what happens in that case? Our current node was 30. So let's say we're adding, 45. Our current node was 30. 30 is not bigger than 45. We totally skipped the body of the if statement. We moved down the list. We set previous equal to current, and we set current equal to current next. Well, current next is my null. And we come back to the top of our loop. So once again, a good exit condition is current is not equal to my null. So someone suggested in the chat, well, current data is less than new data and current is not equal to my null. And that's probably going to work. But as soon as current data is bigger than new dot data, this if loop is going to fire. This if statement is going to fire, and I'm going to kick out of my whole function at that point. Now, if I didn't want to have that return in there, right, I could have that compound statement in my while loop, and then when I come out of the while loop, I could check to see why I came out of it. But again, I don't want to think too hard. To me, I want to do what I want to do, and then just be done, right? So right here, I know I need to insert between previous and current, do the insert, get out of the function. I'm not going to think about it at all. So yeah, basically, while current is not my null is going to work great here. And again, down here I could check to see if current next is my null, because that's also going to kick me out. But I don't want to put this in an infinite loop and try to exit from it down here, because then I've got other edge cases to deal with. All right, so lots of ways to do that. Play around with them, see what makes sense. All right, so we can insert in the middle of our list. That seems like it should work. If we're inserting at the end of our list, that should also work. But we got to add some code for that, right? So if we're inserting our 45, we're going to get to the point where previous is 30, current is my null. We're going to kick out of this loop, because now current's equal to my null. So add to end of list. All right, well, where do we put this 45 in this condition? Right, we basically want to take what we're now calling previous node and change that to point to our new node. So here we can say previous.next equals new. That's going to take this, what was the last node of the list, and have it point to our new node. And then our new node, we need to set the next field, and that should just be equal to my null. And it's worth noting since we know at this point that current is equal to my null, I could have just said new.next equals current. And if I had done that, those two statements are exactly the same as these two statements. Previous next equals new, new next equals current. Right, that's another warm fuzzy moment. So we're doing exactly the same things to insert a node, but sometimes we're doing it in the middle of the list, and sometimes we're doing it, we come out of the loop. But it's the same thing. That parallel structure is suggestive that this is probably pretty close to on track. Sometimes you have genuine edge cases and you have to do something totally different. But that's often an invitation to sort of step back and think from a bigger point of view, a higher perspective. Is there some common theme that would tie these two cases together, right? We don't have to do that. I could have totally different code here. I could probably work and actually find a way to use this code inside here instead of writing my code outside, but don't think too hard, unless you're doing this for fun. All right, so this will add, and since we've added, we'll return a success indicator. So somebody asked a while ago, what happens if we're inserting something before the first node? So suppose we're adding a 5. All right, so we're going to make our node, we're going to set the data to 5. We're going to start off, previous is the sentinel node, and current is going to be this first node. Current is not my null, so we'll come in here and we'll say, is current data bigger than n? Yes, it is. Current data is 10. We're trying to insert a 5. So what does this code say we should do? It says we should take previous next. Well, previous is a sentinel. Previous next should point to new. And then new next should point to current. And hey, that's exactly the right thing. Our sentinel points to the 5, that points to a 10, and everything else is the same. So this actually works in the case where you're inserting into the beginning of the list. And then the last case to check is an empty list. And we always have an empty list to deal with. When you first start debugging, you're starting with an empty list and you're going to add things. If your code doesn't handle that, then you can add 100 things. Nothing goes into the list and you can't debug anything else. So what's our empty case look like? Here's the sentinel. It points to my null. All right, let's say we want to add 10. So we're going to make a new node. We're going to find some index using getNode. We're going to set the data value equal to 10. We're going to seed our loop. We're going to set previous equal to 0, and we're going to get set current equal to previous next, which is my null. All right, and then we're going to go into our loop. It says, well, current is not my null. Well, guess what? Right off the bat, current is my null. So we blow through this loop. We don't do it any times at all. We come right down here to our out-of-loop action, which says add to the end of the list. And what does that say we should do? It says we should set previous next equal to new. Well, previous is the sentinel, so previous next gets set to new. And then new next gets set to my null. And we return. Did we do the right thing? Yeah. The sentinel points to a 10. The 10 says it's the end of the list. We've got a list with one thing in it. So again, you don't have to eliminate edge cases, but if you reason your way through a set of code and then you check it and you find that it handles all of the edge cases, you're probably really good as far as having a good algorithm written up. And we're doing all of this before we ever write any code in the editor, right? Pin this down, convince yourself that this works, debug it, run it on test cases, edge cases, non-edge cases. Get yourself absolutely convinced that this is the right thing to do, and then code it into C, right? This is your Engineering 250 wiring diagram. You figure that out and you make sure that that's totally correct, and then you put all the wires in the proto board, right? You write the statements, you add the semicolons, put in the curly brackets. And now if something is wrong with your program, if you know the algorithm is correct, there's a translation problem in going from here to, you know, if parentheses such and such curly bracket semicolon, right? And that's like, you know, putting a wire in the wrong hole or forgetting to connect the power supply or something. But if you write your program and you run it and it doesn't work, you don't want to be trying to figure out, did I make a problem when I wrote the C code, or do I have a problem in my algorithm, right? You want this to be nailed down first. And then going from here to C is more of a mechanical process. If there's no more space up here, right, when you say get node, you have to check the return value, make sure it's not my null. If there is, then just return 0 from the add function. All right, that's all I got to say on PA1. We're past time, so I'll leave it at that. Bring more questions to class tomorrow, and we'll start digging into our next approach to data structures, which is dealing with dynamic memory in the system. All right, I will see you tomorrow. Have a good afternoon.